I have a question, Dr. Meyer.
Yes, ma'am.
So when we did like the AB plus, or the AS plus B over whatever
Yep.
plus C, why is it that the AS plus B is over S plus 1 squared plus 1, but then the CS plus D is over that all squared?
You have a repeated factor. So the factor that you have here, the basic factor we're working with is S plus 1 squared plus 1, but it's being squared. So you have to remember how partial fractions work when you have a repeated factor. Since that factor is being squared, it's called a repeated factor. The way that you do partial fractions with a repeated factor is the factor and then the factor squared.
Okay.
Okay, I won't write out the details of the partial fractions, but let's do another quick setup one, and we'll just do it with a non-quadratic. So for example, if you have 4 over S plus 2 quantity squared, I need an S plus 2, and I need an S plus 2 quantity squared. My basic factor that I'm working with is S plus 2, and that's what's being squared. This is a really stupid example because A is going to end up being 0, but you get the idea. And then my basic factor is S plus 2. So something with 1 degree smaller on the top is just an A, and then the tops match. So the next one's going to be a B also. Again, this is a stupid example because A is equal to 0 and B is equal to 4. Immediately, it's a dumb example, but that's the setup. That's what it would look like.
Okay, that's helpful. So if you had like, if it was cubed, you would have 3, but it'd be like 1 and 2.
So
okay.
If we had like 2s plus 3 over s plus 1 cubed, so my basic factor is s plus 1. I got to do an s plus 1. I got to do an s plus 1 squared, and I got to do an s plus 1 cubed. And then again, since my basic factor is s plus 1, I would have an a B, and a C.
Okay, that's helpful. I just forgot partial fractions.
Yep, nope, that's okay. Partial fractions is stuff that you guys haven't done for a while necessarily, so good question. Other questions before we go on to higher order differential equations? Anything else? We got one more example to do for the rest of class, but any other questions? Zach, yes.
Why wouldn't in the first example it be BS plus C?
Yep, because the basic factor that you're working with is an S plus 2. So we're going to keep it the same for all of the factors that have an S plus 2 in them. You could, if you wanted to, do a BS plus C. That wouldn't be wrong. It would absolutely work out and it would be okay. But the B is always going to end up being equal to 0. And so we're just going to say we don't need to put that in. So if you did a B times S plus C, that would work. You just have an extra constant to solve for that's always going to be 0. Same thing here. You could do a BS plus something and a CS squared plus DS plus E if you wanted to, but because the basic factor that you're working with is S plus 1, all of the rest of the pieces are going to end up being 0. So you could, you're just going to have more coefficients that you have to solve for. This is the specialness of a repeated factor. Does that help, Zach?
Yeah, that helps.
Okay, cool. Any other partial fractions questions? Any other questions in general, either way? Okay, one more then. Let's do a higher order one. There is a formula in my notes for the Laplace transform of x to the n. I'm not going to write it out. I'm just going to trust that you can find the pattern. So let's just start with an example, and we're going to make sure that we understand where the pattern comes from. X triple prime plus x prime double prime minus 6x prime equals 0. I'll give you initial conditions in just a second. X triple prime plus x double prime minus 6x prime equals 0. X naught is 0. X naught prime is 1. And x naught double prime is also equal to 1. X triple prime plus x double prime minus 6x prime equals 0. X naught is 0, x naught prime is 1, x naught double prime is 1. Let's leave the x triple prime for just a second. We'll come back to that in just a minute, but let's do the Laplace transforms of the other two. So we've got s squared, capital X of s, minus 0s minus 1. That's my transform for x double prime. You should be relatively comfortable with that by now. We've got minus 6 capital X S capital X of S minus 0. That's my transform of x prime. We've got a negative 6 out in front. And then S capital X of S minus 0. Transform of the right-hand side is just 0. Just got a 0 over there. And then if we're following the pattern, here's what I'm going to get for x triple prime. So previously I had s squared. This time I'm going to need an s cubed, capital X of s. And then we just start subtracting and making our powers of s go down. So minus 0s squared minus 1s minus 1. The 0 comes from x naught. The first one comes from x naught prime. And the second one comes from x naught double prime. So the pattern basically stays the same. You just have higher powers that you're dealing with and you're subtracting more things, but the pattern stays pretty much the same. That's why I'm not giving you a general formula, because it's not going to be productive to memorize a general formula. Understand the pattern that's going on and see where the stuff comes from. Okay, skipping the algebra, capital X of s, here's what you end up getting. S plus 2 over S times S plus 3 times S minus 2. So I'm skipping the algebra. You can do that. I'm trusting that you can do the algebra. S plus 2 over S, S plus 3, S minus 2. And I'm going to throw this back to yesterday. We have one extra S, and so therefore we're going to integrate once. I could do this with 3 partial fractions pieces, but I'd like to reinforce what we talked about yesterday. So we have one extra s piece, and therefore we're going to integrate once. So I need to do s plus 2 over s plus 3, s minus 2. I am skipping the partial fractions details. You can find them. This is 1/5 over s plus 3 plus 4/5 over s minus 2. You can find the partial fractions details, write them out. I'm leaving the s off because we're going to integrate as soon as we get done with our answer. So my partial fractions just says 2 pieces. I'm leaving the s off because we're going to integrate. Therefore, the thing to integrate is going to be 1/5 e to the negative 3t plus 4/5 e to the 2t. That's my inverse, and so this is what I need to integrate. I'm going to need to integrate 1/5 e to the negative 3t plus 4/5 e to the 2t. That's the thing that I need to integrate. Are there questions to that point before I do that integral? Okay. Let's go ahead and integrate then. So remember that I need to change the values inside the integral to taus. So I'm going to have integral from 0 to t of 1/5 e to the negative 3 tau plus 4/5 e to the 2 tau d tau. 1/5 e to the negative 3 tau plus 4/5 e to the 2 tau d tau. Constants, when you integrate, are going to give me a negative 1/15 e to the negative 3 tau plus 4/10 e to the 2 tau, evaluated from 0 to t. We can cancel the 4/10 and make it a 2/5, but that negative 3 goes in the denominator and the 2 goes in the denominator. Both of those go in the denominator. When I plug in, I am going to get negative 1/15 e to the negative 3t plus 2/5 e to the 2t minus negative 1/15 e to the 0 plus 2/5 e to the 0. And your coefficient ends up being minus 1/3. So final answer, negative 1/15 e to the negative 3t plus 2/5 e to the 2t, And then if you combine those coefficients in the second part, you're going to get a 1/3 negative. So minus 1/3. Negative 1/15 e to the negative 3t plus 2/5 e to the 2t minus 1/3. So higher order derivatives, and we chose to integrate. Negative 1/15 e to the negative 3t plus 2/5 e to the 2t minus 1/3. If you wanted to, you could have done partial fractions with 3 parts instead of with 2, and then you wouldn't have had to integrate. You could have done it either way. It is entirely up to you. Okay. How are we doing? 2 things for today. If you have an S minus A, and if you have higher order derivatives. We've got 2 minutes left in class. Any other questions that you have at this point? Anybody, anything? No, we're good? Okay. Grant, yes.
Would you quickly be able to explain how to manipulate that top coefficient like we did in one of the examples?
Which top coefficient?
When we did the x double prime plus 6x prime plus 25x equals 20, we manipulated it was 9 over
Oh,
s
yeah,
plus
yeah.
3.
Okay. Yes, I'll do that. If anybody wants to stay and see that, you totally can. I'll share my whiteboard again. If you want to leave, classes over, so you're more than welcome to. But yes, playing when you have a sign, right? Your Grant, when you have a sign of KT, playing with that constant. Yep, I'll share my whiteboard again and we'll do that. Any other procedural questions or anything else? Okay, again, if you want to drop off, you're more than welcome to let me share my whiteboard and we will show you how to manipulate that top constant. So if you're dropping off, that's totally fine. Otherwise, here we go. Let's do a new whiteboard. So let's just do one. I'm just going to make an example up. Let's say that I have 15 over s squared plus 9, okay? 15 over s squared plus 9. So my k value is equal to 3. In this case, that's what my k is going to be. And in the top, therefore, I'm just looking, I want to have a 3. So this needs to be 3 times something over s squared plus 9. That's wrong right now, but that's what I need to have. So I need to have a 3 times something, and this is not a great example because 15 is easily divisible by 3, and you can tell what's going on. Let's do 13 instead. So let's say I have 13 over s squared plus 9 instead of 15. 13 over s squared plus 9. Okay, so I have a 3. I also still had a 13. And then I need to divide by 3 because I multiplied by 3. So we have a 3 that I need. We have a 13 that I had. And then I have a 1/3 that I multiplied by in order to get rid of the 3. So therefore, my inverse transform, little f of t, is going to be 13 over 3 times the sine of 3t. I need the 3 for my transform. So the 3 over s squared plus 9 is the part that goes with my transform. And then the coefficient that I have left is a 13 over 3. Does that help, Grant?
Yeah, I believe so.
Okay, do you want to see one more quick?
Yes, please, actually. Well, because I'm confused because it seems like that top should just be 13 because it just gets rid of the 3's.
It does, but you have to, if the top is just 13, then I wouldn't have a 3 here. I have to have a 3 for my inverse transform. So this right here, the part that's circled, is the part that I need for my inverse transform. And then I have to make sure that my numerator was what I started with. I started with 13. So when I look at my whole numerator, I have to make sure that I have a 13 at the end there. So there's 2 things going on. Maybe this is the easiest way to think about it. You got to have your answer for what you are looking for your inverse transform. And then your numerator can't change. Your numerator has to be the same as what it was before. Is that any better if I say it that way?
Yeah, so could it just be like what our numerator was divided by k?
Yes, but I don't want you to memorize that process. So yes, but let's do another one because I want you to think it through as opposed to memorizing it. So let's do, we'll go back to 15. 15 over s squared plus 4. So my k is equal to 2 in this case, and that means what I need is 2 over s squared plus 4. This is the part that's circled. This is the part that I need. I had a 15 previously, and then in order to make the numerator what I had before, I got to multiply by a 1/2 in order to undo that 2. So inverse transform is 15/2 sine of 2t in this case. Okay.
I think I got it now.
Okay, so yes, the answer is yes, you can just divide by k, but I am much more about process than trying to have you memorize stuff. And so that's why I want you to kind of write it out this way and see what's going on.
Okay, thank you.
Good?
Yeah.
Okay. All right, Aiden, helpful? Yes? Good? Awesome. Okay, I am gonna end then. So thank you guys, and I will see you on Friday.